tiny circle, it should have a fairly high curvature, whereas a big, huge circle, it's big enough, you're traveling along it, it may even feel like it's a straight line at spots. So curvature of a circle should be constant, but as the radius increases, I would expect the curvature to drop. Down to 0. You guys follow my notation. As R increases, I'm expecting curvature to go down to 0, and as R drops to 0, I'm going to expect the curvature to blow up. Those are things I should expect about curvature. I wanted to have something to do with rates of change in this R prime vector, but I really don't care about the length of R prime. What I care about is purely when it changes direction. Does that make sense? Okay. So, given R, R prime is tangential to R, we call the unit tangential vector T to be the following. So it's in the tangential direction to R because it's a multiple of R prime. And dividing R prime by its magnitude makes that vector a unit vector. Is this okay? There will be some exercises in the book that ask you to compute these things. Nobody wants to compute them. You don't need to compute them, really. I mean, they're textbook problems to make sure you understand the definitions. But the reality is mostly what you need is to understand its length 1 and the direction it points tangentially. Call this, it's kappa, Greek letter, Greek K. Call this the curvature. And we are going to define curvature to be the magnitude of the unit tangential vector differentiated with respect to that arc length parameterization. Why the arc length parameterization? I don't think it really matters per se what parameterization people will use, except what I want to do is to get rid of any notion that parameterization is a affecting some way of computing the curvature. And the way to do that is to give a standard parameterization for every curve. And then take this derivative. It's going to give you back a vector, take its magnitude. But because these vectors are all unit vectors, when you differentiate, all you're focusing on is changing direction. You guys see? So what this does is it gives exactly the same parameterization to every curve. And that will have the effect of getting rid of any measurement that in some way is affected by the parameterization. The only problem is it's a pain in the neck to compute with, and I can't usually find out what S is. So what do we get? We get a number of different formulas, and I'm looking for one of these that they don't have that's bugging me. So this makes sense, but it's hard to compute with. And so nobody will use this formula. What instead they're going to do is to use alternate formulas. So we have alternate ways of computing. The alternate methods mean or will provide ways of computing curvature that are entirely independent of that arc length parameterization. Okay? So at this point, let me write down their formulas that they give you here. So this is not the formula you want to work with, but it's the formula which will give the insight into the geometry. The formulas that they give you, I think there's one more real nice one, but this actually works the best. I think most people end up using these. And these are formulas that, if you need them, I will provide them. Not on this test, but on the second test. These are not formulas that you need to memorize. So, a bunch of work goes into deriving this from this. Just a bunch of work. Keep in mind, this does not immediately to me look like it would have anything to do with curvature.
Is that a cross or an X?
That's a cross.
Is that our double prime on
Yes.
the right?
Yeah. So R prime crossed R double prime, take its magnitude, and then divide by the cube of the magnitude of R prime. Why this would have anything to do with curvature, if you looked at it, doesn't at all look like it. I mean, this is kind of like that notion of the dot product, where you've got an easy to compute formula, but you get no insight into why anybody would care to define a dot product that way. You see no geometry in it, but the geometry, the magnitude of A, magnitude of B, cosine of theta, that's where the insight comes from. And that's what's going on here. This is insight, but nobody wants to work with it. And so there's a bunch of manipulation that goes into showing these two are the same. I can do it. I don't think you particularly care for me to do it. I mean, I don't think it adds anything. There is another formula. If the curve is along a function, y equals f of x. Curvature is given by the absolute value of the second derivative of f divided by 1 plus f prime of x squared, raise it to the 3 halves. These formulas are given to you on page 752. These are not formulas that you have to memorize. I will provide if needed. Okay? Example.
What was the page number again? Sorry.
752.
So,
Okay. Example, let's let x of t equal r cosine of t, y of t, r sine of t, and let's let t run between 0 and 2 pi. This parameterizes what?
circle?
Circle of radius r. So this is giving me my circle of radius r. We've said that we would expect the curvature to be constant along the circle and that it be tied to the radius in such a way that bigger radii should have smaller curvature. So my r here is r cosine of t, r sine of t. R prime is minus r sine of t, r cosine of t. And r double prime minus r cosine of t minus r sine of t. This is motion around a circle with constant speed. And if you notice, just generally speaking, this, we're going counterclockwise. This is my r. This going back in towards the center is my r prime. I mean, you can look at r, you can look at r double prime. They're just negatives. And if you dotted r with r prime, you'd get r cosine times minus r sine. Yeah, you get 0. Which is telling you what about r prime? It actually, in this instance, is orthogonal at right angles to r. I mean, none of that is real relevant to what we're doing, but it does bear mention. Okay, so if I look at this formula and compute curvature, the first thing I should do, I guess, is compute r prime crossed with r double prime. Oh. What do we do when we want to cross vectors in 2 dimensions? Cross products are really for 3 dimensions.
The rotations around K? The rotations around the axis K?
I'm not sure I understand what you're answering. Which doesn't mean it's wrong, it just means... I mean, the way in which I would be able to deal with cross products is to throw a 0 into the K component, and then my cross products will make sense. So the cross 2 things, you need them to be in 3 dimensions. Okay, so we cross. The I is going to give me 0. The J, that component is also going to be 0. The K component is going to give me r squared sine squared minus a negative r squared cosine squared. Okay, so r squared sine squared of t minus a minus r squared cosine squared of t, and that is the cosine squared plus sine squared is but r squared.
R squared.
Which means the magnitude of this vector is r squared. In the denominator, I need the magnitude of r prime cubed. So there's r prime, its magnitude is square root of r squared sine squared of t. R squared sine squared of t plus r squared cosine squared of t. Sine squared plus cosine squared is 1. So square root of r squared, or r. Which means, I'll do it once. Which means when you go to take curvature, you're going to take this magnitude divided by the cube of this magnitude. It does not matter where we are on this curve of radius little r, the curvature is constant. The curvature is the reciprocal of the circle's radius, which does just what you would expect. As r gets big, this goes to 0. As r gets closer to 0, the quotient blows up. Okay? Questions here?
So, like, how we see this is, let if or given x of t equals r cosine t, y of t equals r sine of t, and then the t is greater than or equal to 0, less than or equal to 2 pi, you say find curvature.
Well,
Basically.
actually, at this point, if you are asked on a test, what is the curvature of a circle of radius 3,
Okay.
it's 1/3. I've just
Yeah.
computed it.
Yeah.
You know, you guys don't have to go through and do it again. Okay? So, you know, this is at least satisfying that one definition. So,
So is k straight up always going to be 1 over the radius?
if you're talking about
Circle.
a circle,
Yeah. Okay.
yeah. If I'm not talking about a circle, then you've got to go through.
So it's just,
Yeah, and then it's just, you know, just exactly the way I did. So, for instance, if we just let y equal e to the x, where is its curvature the greatest, do you think? It's not going to be constant.
The higher you get,
I don't know. I mean, that's a reasonable guess.
is it the point of inflection?
There is no
No,
inflection
there's not. So
point.
the inflection. Well, what is that? I'm sorry.
No, but no inflection point. There's no change in concavity.
okay,
It's
yeah.
always concave up. It's always increasing.
I'm thinking. Whatever. I guess what I'm trying to think is like the max, like the vertex of the curve.
Vertex is a word used
Right.
with parabolas.
Yeah.
I don't know what the vertex is. You mean the x-intercept? There's no well, there's a horizontal. The curvature out this way should be going to
zero.
zero because it's approaching a straight line.
But doesn't it come to a vertical?
Yeah. So
No,
that's-
there's no
no.
vertical
No,
asymptote
it's
with e to the x. It just blows up, gets bigger and bigger. No vertical asymptote here. Okay, so if we use, we have a function, so we can simply compute this. So y prime is e to the x, and so is y double prime. So curvature would be defined to be second derivative, absolute values, but e to the x is always positive, over 1 plus the square of y prime, so that's an e to the 2x, raised to the 3/2 power. Curvature changes depending on where you are on this curve. x goes to minus infinity, e to the x over 1 plus e to the 2x to the 3/2
Yeah.
goes to 0.
Oh.
So basically what I'm thinking of this denominator for x real negative, e to the 2x is very close to 0. Which means my denominator is very close to 1, which means that quotient is going to be approximated by simply e to the x, which goes to 0 as x goes to minus infinity. I don't know if there's an easier way to look at this. L'Hopital's rule is not going to work here because the e's are never going to go away. So I don't know if this is okay for you guys to see or not. The other issue is what happens as x goes to infinity.
The curvature approach infinity.
I need to look at this. And so as x goes to infinity, I tell you 1 plus e to the 2x is approximately e to the 2x. Huge, add 1, it doesn't do much. So e to the x over 1 plus e to the 2x raised to the 3/2 power. I should say as x is huge, I can make this approximation. So this would be approximated by e to the x on top, on the bottom e to the 2x to the 3/2 power, which is e to the x over e to the 3x, which is 1 over e to the 2x, which goes to 0 also as x goes to infinity. So curvature is going to 0 on both ends. There is therefore going to be a maximum somewhere in between here. And Calc 1 techniques probably would locate that point. But because we're going to 0 on both ends, there's a maximum curvature. Exactly where it is, I don't offhand know, but I know that it exists. Okay? Okay, questions here?
Yeah, I guess if it's okay to ask, what equation would we use to find the maximum curvature?
I probably would let f of x equal this. I mean, this is certainly where I would start. I mean, in general, finding maxes and mins can be a real nightmare. But I would probably start with this and look for critical values. So if I square the denominator, I would have this, and then I bring this up. to the x minus, this is really looking miserable, e to the x, 3/2, that's stuck to the 1/2, and then a 2e to the 2x. I could probably fiddle with it, but I'm sure you guys don't want to sit here while I fiddle with it, so.
We'll just say it's somewhere around where E is itself, so 2.796.
Why? Why? Random guess? Yeah, I don't know. I mean, this isn't impossible to work with because you can do some factoring out. I can fiddle with it and probably find it. I just don't want to. I mean, it's essentially 8 o'clock. So if you want me to finish it, I don't mind.
So
doing
that's it. We just find the
Well, I would need to
the
find the
derivative
critical
of that
value
function.
to get the maximum.
Okay.
So set the derivative to 0. So, I mean, I don't mind finishing it out. I just don't
You said-
want
Yeah. Go ahead.
to. So if you guys feel like you want to leave, that's okay. My feelings are hurt. But I will finish this out, so. Okay, so there's my derivative. Okay?
Yeah.
Okay. To get the critical values, I need to know where this is 0 or undefined. It's never undefined. So for this guy, I'll get my critical value when f prime of x is 0. So that means set my numerator to 0. Okay, so I guess those 2's cancel. What I would do is to factor out of this numerator e to the x times 1 plus e to the 2x to the 1/2 power. So that's going to leave me with 1 minus 3e to the 3x. Okay? And therefore my critical value is when 1 equals 3e to the 3x, so 1/3 is e to the 3x, log of 1/3 is 3x, so 1/3 natural log of 1/3, which is not easy. You know, I mean, you would technically have to show that's a maximum, but you got curvature going to 0 on the left, curvature going to 0 on the right,